Alright guys, we made it to the very last section of Chapter 4, Logarithmic Equations and Applications. In this section, we'll be solving a lot of different kinds of log equations, and at the very end, we can look at a couple of applications. Example 1 says, solve each of the following logarithmic equations. So here comes the first one. Alright, we have log base 5 of 3x minus 1 is equal to log base 5 of x plus 3. Okay, I want you to draw the analogy here from when we were discussing exponential equations. In the previous lesson, whenever we had an exponential expression set equal to another exponential expression with a common base, we drop the bases and set the exponents equal. Well, similarly, because log functions are also one-to-one, if I have log base 5 set equal to another log with the same base, we can drop the logs and just set the arguments equal to each other. Okay, so it's very similar to how we approached exponential equations that have the same base. So again, whenever you have a log set equal to another log and the bases are the same, you can go ahead and drop the logs, set the arguments equal, and solve. Okay? All right, subtract x from both sides. When you subtract x from 3x, you get 2x. Add 1 to both sides. When you add 1 to 3, you get 4. When you divide both sides by 2, you get x equal to 2. Now, you may think we're done, but we're not, because log functions, if you remember the definition from log functions in prior lessons, you'll remember that there are domain restrictions on your log functions. So you always have to remember, this is very important, that when you are done solving for x, to plug it back into the equation and make sure that you get something that's defined, okay? So you're going to see me right now plug x equal to 2 into my original equation, okay? So this is me checking. So log base 5 of 3 times 2 minus 1 is supposedly equal to log base 5 of 2 plus 3. Like that, okay? So this would lead me to log base 5 of 3 times 2 is 6, 6 minus 1 is 5. Log base 5 of 5 is equal to log base 5 of 5. The main thing I want you to look out for is that when you plug in your proposed value into the original equation, you have to make sure that this proposed solution keeps the argument positive. All right, the argument of your log functions. Now, remember that the argument of your logarithms can never be negative. So this has to remain positive. And when I plug 2 in, I do get a positive 5. So we're good here. X equal to 2 is my final answer. Okay, so let me actually do this. So that checks out. And I can say X equal to 2. And now I'm going to box it as my final answer, okay? So each one of these log equations, check your answer, okay? Let's go to the next problem. All right, we have log of x squared plus x is equal to log 6. Okay, guys, log of 6. These are common logs, right? Because the base is not written, so the base is assumed to be 10. Just like the previous example, you have log base 10 of this expression is set equal to log base 10 of that expression. So because the logs are set equal to each other with the same base, we can drop the logs and say, well, this will only be true when x squared plus x is equal to 6. All right? So the approach for solving this equation is exactly the same as the previous. Okay, this resulting equation is quadratic. Because it is such, I am going to set it equal to 0 by subtracting 6 from both sides. I will solve by factoring. It factors as x plus 3 times x minus 2. I will set each factor equal to 0 and solve. So x plus 3 is 0, or x minus 2 is 0. So I get x is supposedly equal to -3 or +2. What I want to do is I want to check these solutions by plugging them into the original statement. And I'm looking out for, I got to make sure that when I plug in these values, my arguments are positive. All right, so that's what we have to check. We have to check to make sure that when we plug in -3, when we plug in 2, the argument is positive. Let's check -3 first, okay? So log of -3 squared plus -3 is supposedly equal to log of 6. This would be log of, now we all know that -3 squared is 9, and then 9 plus -3 is 6. So log of 6 is equal to log of 6. All right? So this definitely checks out, right? So x equal to -3 is a solution. It's now time to check x equal to 2. All right? So we have log of, let's see, 2 squared plus 2, right? That's x squared plus x. It's supposedly equal to log of 6. And again, what I'm looking for mainly is that the argument of my log function is positive. 2 squared is 4 plus 2 is 6. 6 is positive, so we're good, right? So this also checks out. So x equal to 2 is my other answer. So this log equation has 2 solutions. Cool, let's move forward. Okay guys, next problem. Natural log of x plus 1 plus the natural log of x minus 5 is equal to the natural log of 16. Very, 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 very important here. A common mistake I see students do is they drop all of these logs, these natural logs. You cannot do that here. You can only drop the logs if you have one log on this side set equal to a log on the other side with the same base. And you don't have one log on the left side. You have a sum of logs. Okay? So what we're going to do instead is I am going to challenge you to use the product rule from the previous lesson to rewrite this sum of logs here as a single logarithm. The product rule says that this would be the natural log of x plus 1 times x minus 5 is equal to the natural log of 16. So using the product rule, now you can see, now we have only one logarithm set equal to another log. And of course their bases are the same. They're both natural logs, right? Base e. So now is the time where I can drop the logs and just say, well, this is only true if x plus 1 times x minus 5 is equal to 16. I'm just setting the arguments equal, all right? Now don't do that in the prematurely. You have to make sure you only have one log set equal to one other log. Then you can drop the logs. Okay, so let's solve this equation, everybody. Let's FOIL the left-hand side or distribute. You get x squared minus 5x plus x minus 5 is equal to 16. You get x squared minus 4x. I am going to, I just combined like terms. I added negative 5x and positive 1x. At the same time, I'm going to subtract 16 from both sides. When I subtract 16 from negative 5, I get negative 21 equal to 0. I am going to factor this as x minus 7 times x plus 4. Oops, I'm sorry, not x plus 4. That was wrong. X plus 3 is what I should have written, is equal to 0. All right? Set each factor equal to 0 and solve. And you have two proposed solutions. I say proposed because they're not really final solutions or valid solutions until you check them, okay? So we have two values to check, 7 and negative 3. Let's check them now. Okay, guys, I went to the original statement, the original equation, and I plugged in 7 wherever there was a variable. And again, the main thing I want you to look out for is these arguments must be positive in order for x equal to 7 to be a valid solution. Okay, so you end up with the natural log of 8 which is positive, 8 is positive, very good, plus the natural log of positive 2. 2 is positive, so then we're good. Because these arguments right here, that number and that number, are positive numbers, we know that this is good. All right, so once you've shown that the arguments are positive, you are good. X equal to 7, where is it at? X equal to 7 is a valid, solution, all right? So I'm going to come up here and box that answer. Let's check -3 now. Okay, I've plugged -3 in to the original equation, and the main thing I want to check is that these arguments are positive, okay, in order for -3 to be a valid solution. All right, do you see that we're running into a problem here? Because you're going to get natural log of -2, that argument is negative, plus the natural log of -8. This is a problem. The argument, if you refer back to your definition for log functions, the argument must be positive. So this is just telling you that -3, x equal to -3, is not a valid solution. Many times we call -3 an extraneous solution. All right, I've labeled x equal to -3 as an extraneous solution. What this means is this log equation only has one final answer. Okay guys, before we move forward, I just want to recap. This is how we've been solving log equations so far. And I know we're just getting started, but strategy number 1 is, once you have one log set equal to one other log with the same base, you can drop the logs and set the arguments equal to each other and solve. Okay? That's what example 1 was all about. Now we're moving to example 2 and example 3 and more. And the strategy is going to be different, all right? So here we go. Okay, here we go. Example 2, solve the log equation. Log base 5 of 3x minus 1 is equal to 2. The first thing I want you to notice is how this equation is different than all of the equations in example 1. It's different in that you only have one log on the left-hand side, and you don't have any logs on the right. It's just a number. It's just a constant. So here is our strategy, guys. You're going to love this. You're going to love this. Remember in earlier lessons when we were studying logarithms, we said that we can always write a logarithm expression in terms of its related exponential expression. So we did something like this. Base 5 raised to the power of 2 gives me that argument. Do you remember making that little tail in previous examples or previous lessons? So then this is the same thing as 5 squared, 5 raised to the power of 2, will give me 3x minus 1. This is the related equation. That is to say 25 is equivalent to 3x minus 1. And all you have to do is solve this equation now. Add 1 to both sides. You're going to get 26 over there. And divide both sides by 3. So 26 thirds is equal to x. That is to say, x is 26 thirds. Now, we're going to check this answer because we have to, right? Now, do you remember what I was saying? I was saying the main thing we're checking is that when you plug in 26 thirds, which is the proposed solution, that your argument is positive. So why don't we just focus on this argument? I don't have to write down everything. Let's just take the argument, plug in 26 thirds right here, and confirm that you get a positive argument. So I'm only going to focus on my argument, okay, everybody? So 3 times 26 thirds minus 1, like that, okay? And I'm only checking to see if my argument is positive. These 3's divide out, right? And you get 26 minus 1, which is positive 25, which is a positive number. So we are good. We can confidently say 26 thirds is the one and only solution for this equation. All right, guys, example 3, log of x minus 1 plus log of x plus 2 is equal to 1. Again, do not use strategy 1. Do not use strategy 1, which says that you can drop the logs. You can't do that here because you don't have one logarithm set equal to another log, that you don't have that. You have a sum of logs equal to just a number. Okay, so this is what I'm going to challenge you to do. I'm going to challenge you to use the product rule here from earlier lessons to rewrite the sum of logs as a single log. So you are invited to pause the video and try to rewrite these two logs as a single log. I hope you did that. You would get log of x minus 1 times x plus 2 is equal to 1. That's the product rule for logarithms. Now, I'm going to invite you now to do the same thing we did in the previous problem. Change this to its related equation. So base 10 raised to the power of 1 gives me all of that argument. Okay? So then this is base 10 raised to the power of 1 gives me x minus 1 times x plus 2, like that. Cool? So then this is 10 is equal to, distribute this, you get x squared plus 2x minus x minus 2. Okay? Because this is quadratic, I am going to set it equal to 0. I'm also going to combine these two terms here. 2x minus x gives me just 1x. So then you're going to get x squared plus 1x. And then when I subtract 10 from negative 2, I get negative 12 and set this equal to 0. All right, I'm going to solve by factoring. Factoring it as x plus 4 times x minus 3 equal to 0. Set each factor equal to 0 and solve. And so you get two proposed solutions of negative 4 and positive 3. Okay? Good job, everybody. So now it's time to check. All right, remember when we check, everybody, let me scroll back up here to the original problem. Here it is. The original problem has this argument, x minus 1, and this argument, x plus 2. I'm basically going to be plugging in our proposed solutions into these arguments and making sure that these arguments stay positive. So let me take each argument one by one, okay? The first argument is x minus 1. Let me plug negative 4 into x minus 1, okay? So this is the first argument, x minus 1. And when I plug negative 4 in for x, I get negative 4 minus 1, which is negative 5. This is negative. The argument can't be negative. So this is a big problem. So therefore, I don't even have to check the other argument. Who cares what the other argument is? Because this argument has already proven to be a negative argument, which is not okay for log equations. So what does that mean? Well, that means that x equal to negative 4 is an extraneous solution. That word extraneous just means that x equal to negative 4 is a solution of the manipulated equation, meaning this equation here is the manipulated equation. Negative 4 does satisfy this equation, but it does not satisfy the original. Okay? All right, so that is done for negative 4. Let's now check the other proposed solution, all right, which is 3. Okay, one of the arguments is x minus 1. I'm going to plug 3 in, and I get positive 2. So that's good. That's good. But there's another, let me go back to the original. There's another argument that you have to check, okay? And I know you can probably do this in your mind. You can probably visually see that when you plug in 3, 3 plus 2 is positive 5, so we're good. But let me actually just, for the sake of teaching this, show you that. So the other argument is x plus 2. So when you plug 3 in, you get 3 plus 2, which is positive 5. That argument is positive. Both of these are positive. So then this checks out. X equal to 3 indeed is a valid solution for this equation. So this equation only has one valid answer. Okay? Okay, before we go further, I just wanted to recap. So we have strategy number 2 that we've been using, and that is if you have one log equal to a constant, when I say a constant, I mean just a number, then you can rewrite the equation as an equivalent equation without a logarithm. And that's basically doing that little tail trick. In an earlier lesson, I called that like the little tail or scorpion tail trick, where you rewrite it as its equivalent expression or equivalent equation. Okay, so we got strategy number 1 and strategy number 2. Okay, all right, so we just used strategy number 2 for examples 2 and 3. All right, so now let's continue. Okay, here are both of those strategies for you, just in case you need to see them, all right? Here's your brand new example for solve the log equation. When I inspect this equation, I see that I can use strategy number 2, because I have 1 log equal to a constant. So I take my base. Do you remember what your base is? Because this is a natural log, your base is e. So e raised to the 3rd power gives me all of that argument. So then you're going to have e cubed is equal to x plus 7. Don't worry about finding out what e cubed is. You can keep that as an exact number, okay? You don't have to punch that into the calculator. Solve for x here. X is your variable, so subtract 7 from both sides. When you subtract 7 from e cubed, you just have e cubed minus 7. That's it. So this is the solution for x. All right, for the checking process, remember we have to confirm that when we plug in our solution, or our proposed solution, e cubed minus 7, and for this x right here, this entire argument must be positive. Okay, keep this in mind. E cubed minus 7, if you actually do punch it into the calculator, it's about 13.09. Okay, that's what this proposed solution is about. So then when I plug that number, I know that's an approximation, but it's a close approximation. When I plug it into my argument, like that, this is a positive number. Actually, I could just write it if you'd like. This is about 20.09. But the big idea here is that this argument it is positive, all right? So then this proposed solution does check out as a valid answer, okay? All right, here's our brand new example. Log base 2 of x minus 1 minus log base 2 of 5 is equal to log base 2 of 7. Okay, I don't know what your initial thought is, but my initial thought is let's use strategy number 1, which says that if you have one logarithm set equal to one other logarithm with the same base, then you can drop your logs and set the arguments equal to each other and solve. The problem is I don't have just one log on the left. I have a difference of logs. But you should remember from earlier lessons that a difference of logs can be rewritten using the quotient rule as a single log. So if you use the quotient rule, this is going to be log base 2 of the first argument is your numerator, and the second argument is your denominator, like that. And so now, thanks to the quotient rule, we do have just one log base 2 equal to one other log base 2. So by strategy number 1, we can drop the logs and say, well, this is only true if x minus 1 over 5 is equal to 7. Like that. Okay, solve for x. I think what you can probably do to both sides is to multiply both sides by 5. Multiplying both sides by 5 will get rid of your fraction, right? So it'll do this for you. These 5s cancel, right? And then you would have x minus 1 is equal to 35. Add 1 to both sides. So adding 1 to 35 would give you 36. Cool? Let's check our answer. I'll remind you that when we check, we just want to make sure that the arguments in the original statement are positive when you plug in 36. This argument is without question a positive value, so we're good. This argument is without question is a positive value. It's just this one that we have to check, right? So when I check, I am checking x minus 1, right? That argument. When I plug 36 in, this is pretty straightforward, right? You get 35. 35 is a positive number, so then we can confidently say x equal to 36 is valid. You know, by the way, if 36 happened to be not valid, if it happened to be extraneous, your final answer would be what? No solution. Because this was my one and only proposed solution, and if it turned out to be bad, there is no other solution being proposed, so it'd be no solution. All right, cool. Let's go to the next example. All right, example 6. Log base 2 of 3x minus 2 is equal to log base 2 of 5x plus 1 plus 3. I just want to make sure that we're all on the same page, that you cannot use strategy 1 to drop these logs here and set the arguments equal. The reason is because although you have log base 2 equal to log base 2, you also have a plus 3 on the back end. If that plus 3 were missing, if it was not there, then you can drop the logs. Okay? So my strategy here is to get the logs on the same side. I can do that by using subtraction. If I subtract, let's say, this log from both sides, it would bring it over to the left. And then your equation would look like this. Log base 2 of 3x minus 2 minus log base 2 of 5x plus 1 is equal to positive 3. Okay? Now, what do you think we should do? Do you see that you have a difference of two logarithms here? And by the quotient rule, we can write this as one log. So log base 2 of 3x minus 2 over 5x plus 1 is equal to 3. And then at this point, because you have one logarithm equal to a constant, you can use strategy 2. 2 raised to the power of 3 gives me my argument. So this would be your equivalent expression, equivalent equation, I should say. All right, cool. When I simplify 2 cubed, I get 8. So 8 is equal to 3x minus 2 over 5x plus 1. All right. What you can do is you can clear the fraction, this equation of fractions altogether, if you just multiply both sides by this denominator, 5x plus 1. Multiply this side, that side by 5x plus 1, and multiply this left-hand side by 5x plus 1 as well. Like that, okay? All right, let's see. This right-hand side, no more fraction. The left-hand side, distribute 8. So you get 40x plus 8 is equal to 3x minus 2. What kind of equation is this? It's linear, right? So because it's linear, I am not setting this equal to 0. Instead, I am getting all my variable terms on one side and my constants on the other. If I subtract 3x from both sides, I'll get 37x on the left. If I subtract 8 from negative 2, I get negative 10. If I divide both sides by 37, I get negative 10 37ths, which is my one and only proposed solution. Okay, it is time to check our answer, all right? So let's go and check. Now, again, I'm going to remind you that when we go to check, really all we're doing is checking the to make sure that the arguments remain positive. So let me, I accidentally moved that there. Let me scroll up to the original statement. These are the arguments I'm checking. 3x minus 2 and 5x plus 1. I'm going to plug in our answer, our proposed answer, right? I'm going to plug them into each one of these one at a time and confirm that that argument is positive. Let me start with this one, 3x minus 2, okay? 3x minus 2, okay? 3x minus 2. I'm going to plug in our proposed solution. Okay. Does this turn out to be negative? Let's see. You got negative 30, because 3 times 10 is 30, over 37 minus 2. Hey guys, when you have a negative number, and then you subtract another number, don't you get negative? Aren't you still negative? So this is a negative number. That's a problem, that your argument, 3x minus 2, turns out to be negative when you plug in your proposed solution. So what does that mean? That means this answer, negative 10/37, is extraneous, right? Again, what that means is that negative 10/37 satisfies the manipulated equation, but not the original. Okay, I called it out earlier. This is our one and only proposed solution, and it does not satisfy the original equation. It's extraneous. So then what is your final answer then? Well, your final answer is going to be no solution, because the one and only solution that you got doesn't work, right? So then this is your final answer. No solution. Cool. Okay, guys, example 7. This is, just FYI, this is our last log equation that we'll solve. And then we'll look at an application or two. All right? So here we go. Log base 5 of x plus log base 5 of x minus 3 is equal to 1. Okay, let's go for strategy number 2. Let's combine these two logs using the product rule for logarithms to rewrite it as a single log. So log base 5 of x times x minus 3, this is the product rule, is equal to 1. So here you can rewrite it as 5 raised to the power of 1 gives me my argument, right? So then you'll have 5 raised to the first power gives me x times x minus 3. 5 raised to the first power is 5. And then when you distribute this x, you get x squared minus 3x. Because this is a quadratic equation, I'm going to set it equal to 0 by subtracting 5 from both sides. There. You know, this doesn't factor, so factoring is not going to work for us. Let's use a different method. You got a couple options. You can use completing the square process, or you can use the quadratic formula. Let's use the quadratic formula. I think a lot of students, when we were meeting face-to-face, preferred, I remember you preferring the quadratic formula. So the quadratic formula, remember, it's, if you need to remind yourself of what it is, it's negative b plus or minus the square root of b squared minus 4ac all over 2a. So it'll be negative 3 minus, or plus or minus, excuse me, plus or minus the square root of b squared minus 4 times 1 times negative 5 all over 2 times 1. Okay? This is negative b. Your b value is negative 3. So it's negative b. So this turns out to be positive 3 right there, right? So then x is equal to positive 3 plus or minus the square root of 9. I always do this. I count my negatives right here. 1, 2 negatives. 2 negatives make a positive. So it'll be plus 20. 4 times 1 times 5 is 20. All over 2. So then x is equal to 3 plus or minus the square root of 29. And then all of this over 2. Like that. These are irrational solutions, okay? All right, before we box them, there's two different solutions here, 3 plus root 29 over 2 and 3 minus root 29 over 2. We have to check before we box anything, right? You're used to this already. So let's check our answers, all right? Okay, cool deal. Okay, again, I want to remind you that when we check our solutions, we're going to plug our solutions into, our proposed solutions into the original equation and verify that the arguments are positive. Let me scroll up and remind ourselves, including me, what these arguments are. One argument is simply x. The other one is x minus 3. X and x minus 3. Those are the arguments we're checking, okay? Now, we have to check each solution separately, okay? So the first one that we're checking is the first answer we're checking is 3 plus root 29 over 2. Now, if you punch this into the calculator, punch in root 29, and then add 3 to that, and then divide all of that by 2, you get approximately equal to 4.19, about that much, okay? Do you remember what the two arguments are in the original equation? One argument was x. So when we let x be positive 4.19, I mean, that checks out. That argument is positive. The other argument is x minus 3. Oops, sorry about that. The other argument is x minus 3. So when we plug in 4.19 into x and we subtract 3, we get something positive. We get what? About 1.19, which is a positive number, right? So then it checks out of both. So for sure, 3 plus root 29 over 2, 3 plus root 29 all over 2 does work. It absolutely does work. Let's check the other number. Now, the other proposed solution we're checking is 3 minus root 29 all over 2. Now, punch that into a calculator, and that's approximately negative 1.19. All right, so look at this. We run into a problem immediately. One of the arguments in the original equation is x. So if we let that argument, x, be negative 1.19, we immediately get something that doesn't work. It's undefined. So this doesn't work. It also won't work out on the other argument either. But once I find one argument that doesn't, or makes it, once I find one argument that turns negative after substituting in my proposed solution, that's enough to say this is not going to work, okay? So a big like, nah, it doesn't work, okay? So then my one and only solution was 3 plus root 29 over 2. This is my one and only answer, all right? That makes this one, by the way, extraneous, right? 3 minus root 29 over 2 didn't work, so it's extraneous. All right, cool. Okay, the last example or two are going to be applications of log functions. I want to remind you of a formula that we have that we've already seen, and that is this formula here, right? This is for interest that is compounding continuously. Now, what I would like to consider is if you were being asked to solve for the rate, like the rate where it was unknown or time was unknown, then you would probably solve this using some of the methods that we're just using in this lesson. In other words, what you would do is you would isolate R or T, whichever one you were trying to find. The first thing you would probably do is, watch this, divide both sides by P. P is just a number, right? And so these P's divide out there, and you would get A over P is equal to E raised to the power of RT. Now, if you wanted your power to come down, you would have to take the natural log of both sides. Like this, right? And then the power can come down. So then you have the natural log of A over P is equal to R times T times the natural log of E. And don't forget that the natural log of E is just 1, right? So then this is the natural log of A over P is equal to R times T. Now, depending on what it is you're looking for, you can solve for either R or T. If you solve for R, then you would divide both sides by T, and you would get the rate is equal to the natural log of A over P, and then that divided by T. If you were looking for T, if T was your variable, then you would write in this statement here, you would divide both sides by R. So then if you did that, time would be equal to the natural log of a over p, right? And if you divide both sides by r, you would have over r. So what we just have now here is we have a way to find the rate and we have a way to find time, okay? Now let's look at example 8, which is our first application. Okay guys, I'm excited about this one. Example 8, what interest rate would be needed in order for $800 to grow to $1,120 if compounded continuously for 5 years, okay? All right, what are you looking for? What interest rate? You're looking for the rate. So this is the formula we're going to use. You started with $800, right? And it's growing to $1,120. So 800 would be your P value, and the account balance 1120 would go in for A. And then time is 5. Okay, so let's use this formula. Cool. I plugged everything in. I plugged in the our A value, right, 1120, and I plugged in the principal amount, 800, and I'm dividing by 5 for 5 years. All right, let's figure out what this is. Plug all of this into your calculator. Just do the natural log of this fraction here, and then press equals maybe, and then divide it by 5. Okay, I say maybe just because a lot of our calculators are different. All right, so let's see what this rate is giving us, or what rate this is giving us. All right, so when we plug all of this in, this is about 0.0673. Do you agree with that? Which, of course, we want to write our rates as a percentage. Whenever you change a decimal to a percentage, you just move the decimal twice to the right. All right, so then the final answer is approximately 6.73%. That's what the rate would have to be approximately. Okay, everybody, 6.73%. That was really cool, wasn't it? All right. Okay, guys, last example. How long would it take for $750 to grow to $990 if compounded continuously at 4.5%? I hope it's clear to you that we are looking for time. How long? How long? So we're looking for time. So let's use that formula from a little bit before, a few minutes ago, for time. This is the formula that we derived earlier, all right? So let's just plug in everything that they gave us. So time, it's going to take this long. The natural log of, now remember A stands for like your ending balance. So you want your money to end up at $990. P is the principal, which is the starting amount. So you started at $750. That's P, and divided by the rate. But just be careful, the rate must be written as a decimal, right? Here, I'll do it over here just to make sure that we're all clear. 4.5%. Drop the percent symbol, and then drop the percent symbol, and then move this decimal twice to the left, right? So then as a decimal, 4.5% is 0.045. So just be really careful about that, okay? So 0.045. All right, let's plug all this into the calculator. Okay. All right, everybody, good job. This completes this section, 4.7, log equations and applications, and this completes all of chapter 4. So we are finally done with chapter 4. It's been an amazing chapter, full with tons of information. It's been really fascinating. I hope you've enjoyed chapter 4. All right, everybody, I'll catch you soon in another video.